I apologize for my sore throat. My voice is very, very low, but if you can hear, it's well for me. This presentation aims to give an overview of how the second generation of Eurocode 2 accounts for the influence of axial forces on the shear resistance of members without shear reinforcement. First, I will talk about the general model to calculate the shear resistance in presence of compressive or tensile axial forces. Then I will explain the linear approach. I explain the basis of the linear approach, and this linear approach allows to calculate the shear capacity without iteration and without iteration, but only for compressive axial forces. On the other hand, we will highlight the main improvements of these two formulations, the general model and the linear approach, which provides better agreement with the experimental results than current EC2. And finally, we'll summarize the main conclusions. The general formulation is based on the power law shear failure criterion of the critical shear crack theory, according to which the shear resistance is a power function of the reinforcement strain. This function is parametric with the effective shear slenderness. In the figure, we have shown the power law for the values 1, 2, 3, 4, and 6 of the effective shear slenderness. And for comparison, the hyperbolic law and the test results. The reinforcement strain can be calculated by a simplified flexural analysis of the crack cross-section. When there is no axial force acting on the control section, the reinforcement strain is proportional to the applied shear force. And then the load deformation path is a straight line that passes through the origin. The intersection of this straight line with the shear failure criterion gives the shear resistance and can be formulated by a closed form equation whose format is like the current EC2 formulation. When an axial force acts on the control section, the reinforcement strain is, can be evaluated taking moments at the point A of the section. And so the load deformation path is a straight line that does not pass through the origin. The intersection of this straight line with the shear failure criterion does not provide a easy to use formulation. To obtain a an easy to use formulation of the shear resistance, the reinforcement strain is expressed as proportional to the applied shear force multiplied by the effective shear span accounting for the axial force. This is the length of the effective shear span where the reinforcement is in tension. And this length is given by multiplying the effective shear span by the coefficient KVP. Coefficient KVP, of course, is a function of the applied shear force by also by the applied shear force, the axial force and the applied shear force. So, given the value of the applied forces, the coefficient KBP can be calculated. And from this value, the load deformation path is a straight line that passes through the origin. This straight line is of different slope than where there is no axial force. The intersection of this load deformation path with the shear failure criterion provides the shear resistance and can be formulated as when there is no axial force by a closed form equation where the influence of the axial force are accounted for by the coefficient KBP and the mechanical shear span instead of adding a term. The general model can be easily used for verification problems. So given the applied forces, the values of KBP and AB can be calculated easily, and the shear resistance can be obtained by the closed form equation. Note that different values of shear resistance are obtained for different values of applied forces. However, it can be stated that if the shear resistance is less than the applied shear force, the section fails. On the contrary, if the shear resistance is greater than the applied forces, the section is shaped without having to calculate the shear capacity. To calculate the shear capacity, the applied shear force must be replaced by the shear resistance in the KBP and AB. And so the closed form equation becomes a nonlinear equation that have to be solved by iteration. To avoid this iteration, the new Eurocode 2 provides an alternative formulation that is based on linearizing the shear resistance axial load relationship provided by the general model. The linear function is a straight line that passes through the point A and the point B. The point A corresponds to the shear resistance for zero axial force, and point B corresponds to an axial load that makes zero the reinforcement strain for an applied shear force equal to the maximum shear resistance. The maximum shear resistance can be obtained by the general model, the closed form equation, by taking the minimum value of the KBP and AB. In these conditions, the slope of this straight line is the difference between the maximum shear resistance and the shear resistance without considering axial force divided by the maximum axial load. Since this difference of the shear resistance is about 0.5 times the maximum shear resistance, the Kn, this slope, can be expressed by a function that depends on the eccentricity of the axial load to effective depth ratio and the effective shear slenderness without considering axial force. The linear approach expressed in terms of stresses makes explicit the dependence of the section shape on the shear resistance by the factor total cross-section area divided by the web area. Both formulations, general model and linear approach, accounts for three variables whose influence on the shear resistance in pre-stressed concrete beams are experimentally demonstrated: the shear slenderness, the eccentricity of the axial force, and the cross-section shape. Any of these variables are taken into account in the current EC2 formulation. These three formulations are verified by 183 tests from a database on simply supported pre-stressed beams, 85 of rectangular cross-section and 98 of profile cross-section. The table and graphs show the range and frequencies of the main parameters of this database, which are the effective depth, the shear span, the eccentricity of the axial force, and the compressive stress. These three graphs show the experimental to calculated shear resistance for the three models, the Eurocode 2, the current Eurocode 2, the general model, and the linear approach. It can be shown as the coefficient of determination R squared for the Eurocode 2 is 0.76, while for general model and linear approach is 0.88. This shows the better agreement of these two models to the experimental results than the current EC2. In summary, we can highlight the main conclusions. The general model is easy to use for verification problems in presence of both compressive and tensile axial forces, but needs iteration to determine the shear capacity. However, the linear approach allows to calculate the shear capacity with iteration, but only applies for members subjected to compressive axial forces. This linear approach has a similar format to the current EC2 formulation and is consistent with the general model because it's derived by linearizing this model. And finally, both models, general model and linear approach, are in better agreement with experimental results than the current EC2 formulation because they account for the shear slenderness, the eccentricity of the axial force, and the shape of the section. Variables that are significant on the shear resistance in presence of axial forces, but that are not considered in the current EC2 formulation. Thank you for your attention.